Thank you all for joining us today for the April edition of the IPIC Webinar Series. Today we are fortunate enough to have two presenters with us. We have Dr. Meredith Petersen and Dr. Jeff Zimmerman. Dr. Meredith Petersen is the Director of Swine Health at the National Pork Board. She previously worked as a postdoc research associate with the Swine Medicine Education Center, also known as SMEC, here at Iowa State University. Today, Meredith is presenting her PhD research that she completed with SMEC on telemedicine in swine. Then we'll have Dr. Jeff Zimmerman, who is a professor in the Department of Veterinary Diagnostic and Production Animal Medicine, VDPAM, here at Iowa State University, working in swine infectious disease diagnostics, epidemiology, and economics. Today, he is presenting recently published research on new approaches to regional surveillance. So we will start with Meredith first, and then hand it over to Jeff. Just so everyone is familiar, please put all of your questions in the chat, and we will address all the questions after both presenters have gone. So with that, Meredith, I'll hand it over to you to start.
Perfect. Are you able to see that?
Yep, you're good.
Okay, sounds good. Well, thank you for that introduction. Like Stacy mentioned, I'm going to chat about the telehealth work that I did while I was doing a postdoc with SMEC. And so kind of a bit of background. So there's a lot of potential for veterinary telemedicine. Particularly, it could increase our surge capacity for a foreign animal disease outbreak, both of getting more eyes on the pigs, but also of more samplers. Could also improve veterinary medicine access as well as increase teaching efficiency, getting more vet students in front of cases virtually when they would otherwise be in the classroom. However, there are gaps in current research, and we have a real risk of using unvalidated techniques if we don't do the research on them. And so that's kind of what these research projects will hopefully provide some information on the capabilities and limitations of telehealth with pigs specifically. So when it comes to telehealth, there's really a few logistics and pieces of technology to think about. The top three would be software, hardware, and connectivity. And each of these things impact video and photo quality when you're doing a telehealth consult. And so probably the biggest challenge is connectivity. It can have unpredictable fluctuations. And so whatever software platform you use, so for example, today we're using WebEx, but if you're using a telemedicine platform like VetNow or you're using Zoom, whatever platform you use uses a codec, which is a compressor decompressor that basically transfers the video in a smaller packet from one end to the other. And that codec can change based on the bandwidth provided. And so pretty much it's at the mercy of whatever your connection speed is, which can vary greatly throughout a call. And so that bandwidth can fluctuate throughout the day. It varies in real time. And then it's affected by network overload and weather. So that's really kind of a key challenge to telehealth and something that sometimes we can't overcome. And we can't do a live video connection, and then you might need to look at doing something asynchronous or sending videos and photos. A little bit of background on the legal implications of veterinary telemedicine. So the current federal veterinary client-patient relationship, or VCPR, basically states that you cannot create that solely via telehealth. You can use telemedicine within an existing relationship, so within an existing VCPR, but it can't be created solely via telemedicine. However, the landscape around state VCPRs is variable and rapidly changing. So most recently, we've seen California and Arizona adopting or allowing for a virtual VCPR to be created. So that's something to keep in mind. You want to make sure that anything you do is within the confines of what we can do legally. And so in veterinary medicine, and particularly in production animal medicine, telehealth kind of covers any technology related to healthcare. And so things like precision livestock farming technologies, remote monitoring and sensors, those would all fall under telehealth. Telemedicine specifically is actually delivering diagnosing and treatment recommendations to a patient. And so for production animal medicine, as I mentioned, we have a lot of precision livestock farming technologies. AABP has had telemedicine content at their conferences. And really the poultry industry has kind of paved the way in terms of using telehealth. So there's a large company that uses telehealth for remote customer service audits or customer service visits. And then here in Iowa, IDALS has done biosecurity audits virtually to repopulate flocks and houses within a control area for the high path AI outbreak. In swine medicine specifically, pigs are used extensively for models for human telesurgery techniques, but we really don't have a lot of research or information on telemedicine techniques in the field specifically for swine medicine. Last year, AASV released a telemedicine position statement that supports the use of telemedicine within an existing VCPR. It outlines the potential benefits of telemedicine, and then ultimately states that telemedicine should be at the discretion of the swine veterinarian. So it really should be that that VCPR relationship, the relationship between the veterinarian and the producer, to decide when that's appropriate to use. In terms of swine, telehealth could really help meet a critical need. And so in 2023, there were 831 American Association of Swine Veterinarian members in the United States. And there were 75 million hogs and pigs. And so that's, if you do a little math, that's over 90,000 pigs for each swine vet in the US. And I think that number is vastly underestimated for the swine vets who really are truly overseeing the health of the pigs every day. So for example, I'm a AASV member, but in my role at National Pork Board, I don't have direct pigs under my care. And so I think those swine veterinarians who are in the field every day likely are overseeing more pigs than this number represents. Dr. Rodemaker presented at the most recent AASV conference on the early career AASV member attrition study, which indicated work-life balance as a driver for leaving swine medicine. And so I think telehealth really has the potential to more efficiently use some of these veterinary resources and be a solution to a problem, but it needs to be validated through research. So we need to know what it can and can't do. And so with that kind of background, I'd like to share a few research studies that I did as part of my PhD work to hopefully fill in the gaps of use cases for telehealth. So the first project we're going to chat about is an evaluation of in-person versus virtual instruction techniques for training naive students on blood and oral fluid collection in nursery and finishing pigs. So a little bit of background, virtual instruction can have value when there's biosecurity or logistical risks that don't allow for the trainer and the student to be on farm at the same time. So the objective of this study was to evaluate pre and post-training objective structured clinical exams. So that I'll refer to that as an OSCE on blood and oral fluid collection for 3 different training techniques. And so I'll kind of get into what that looked like in the coming slides. So we trained 59 students how to collect blood and oral fluid by one of 3 techniques. So the first technique was in person, where the instructor and the student were both on farm, a pretty standard training how you would normally envision it. The second was virtual instruction using a tablet. So the student was on farm, had a handheld tablet. We did have personnel on farm that kind of held the tablet and videoed for them, but the instructor was in the office, not on the farm. And then the third group was virtual instruction using smart glasses. So we put a pair of smart glasses on the student who was on the farm, and then the instructor was not on the farm, was in the office, and communicated with the student that way. We then trained the students using a standardized training. So we used the certified swine sample collector materials. Those are publicly available on the Secure Pork website, and that's how we trained all the students using the same technique. And then the way we evaluated them was through that OSCE. So an OSCE, or an objective structured clinical exam, is basically a way to give a number or a score to how well a student does a clinical skill. So it's frequently used in things like surgery training or clinical skill training. And so they took that OSCE exam before the training and after. So we had a number or an improvement that we could look at across those three groups. All of the pre-training OSCEs confirmed that the students were naive. So we made sure that they didn't know how to collect the sample before the training. So in terms of success across blood collection, so again, across the top here, we had the 3 treatments. So 19 students were trained in person, 19 were trained using virtual instruction with tablet, and 19 were trained using the smart glasses. When we look across the 3 groups, so average improvement in OSCE score for in-person was around 9, virtual instruction with a tablet was 8, and virtual instruction with smart glasses was 9. And then the number of successful post-training sample collections. So this was the number of students out of 19 that successfully collected blood after the training. So 16 of the 19 in-person were successful, 12 of the 19 virtual with a tablet were successful, and 13 of the 19 virtual with smart glasses were successful. Although these numbers look a little bit different, they were not statistically significantly different from each other. If the students were successful at collecting blood, we then allowed them to attempt 10 unassisted blood draws. So we would restrain 10 pigs for them. We wouldn't give them any instruction, any assistance if they had already demonstrated they collect the sample, and they were able to attempt to bleed those 10 pigs. An attempt was considered 2 pokes, just for the welfare of the pigs. If they didn't get blood in those 2 pokes, it was considered an unsuccessful attempt. And so you can see here on this chart that for all 3 groups, the average success over the 10 attempts was between 6 and 8. And there was no differences between the 3 training methods and how well those students retained the skill. About half the students were trained on blood collection in small nursery pigs that were manually restrained, and half the students were trained in larger finishing pigs that were snared. And you can see that had a significant impact on success. And so on the left here, you can see the percentage of successful blood collections for manually restrained pigs was 83%, and the snared pigs was around 60%. That also impacted their success over the 10 unassisted attempts. And so again, we saw that the students who bled pigs on manually restrained pigs were more successful, or 8 out of the 10 attempts versus about 5 out of the 10 attempts for those that bled snared pigs. For oral fluids, a little less interesting, but good results. So all students were successful at collecting oral fluids after the training, regardless of method. So we didn't do statistics on this because each group was successful regardless of the training method. So in conclusion, we demonstrated successful transfer of clinical skills, both blood and oral fluid collection, via 2 novel virtual instruction techniques. This can be considered when in-person training isn't available. We did see significant impact of restraint method. So pig size, those manually restrained pigs, students were more successful at collecting blood on them than a snared larger pig. So this should just be accounted for when training individuals, that it might take them a little bit longer and more attempts to learn how to bleed a snared pig versus a manually restrained pig. So the second project kind of dug deeper into the comparison of in-person and telemedicine techniques, specifically for observing site evaluations as well as pig evaluations. And so there's a lot of industry interest in using telemedicine for site evaluations and herd evaluations. But as I mentioned before, there's really a kind of a gap in research comparing the in-person evaluation to a telemedicine evaluation. So there were 2 objectives for this study. The first was to evaluate records, ventilation, feed, and water at commercial wean to finish sites using telemedicine. And the second was to compare an in-person health assessment of the pigs to a telemedicine health assessment of the pigs. So having 2 veterinary health assessments of the pigs and understanding how well those agreed with each other. So I'll first kind of talk through the site evaluation component. We visited 20 wean to finish sites via telemedicine by 3 or 4 evaluators for a total of 70 evaluations. So 70 individuals went through a wean to finish barn and filled out a standard evaluation form to evaluate records, ventilation, feed, and water. This is what the evaluation form looked like. So we had our 4 areas of interest, and then under each of those, we had specific characteristics that we asked the veterinarians to review. So that were things like mortality records, treatment records, specifics on ventilation, number of fans, inlets, specifics on feed, what type of feed was being used, and then water, where we looked at water availability and water type. So each veterinarian recorded their interpretation. For example, if it was mortality, they may have recorded, been looking at the records and say, okay, I see that there were 2 mortalities last week. They then confirmed accuracy by asking the person that they were connected to at the farm if that was a correct interpretation. So we look at the results for site evaluation. Across the bottom, you can see all the criteria that we evaluated. And then on the y-axis is the number of interpretations. So each bar goes to 70. As I mentioned, we had 70 evaluations. If it's blue, that means it was correct interpretations. Red was for incorrect interpretations. And the green color was for unable to interpret. And really the takeaway from this slide is that across all the different criteria, we had 90% or typically more than 95% correct interpretation. So we were highly successful at capturing this information using telehealth. Then we'll talk about the pig evaluation component. So again, we visited 20 wean to finish sites via telemedicine. Those were our telemedicine evaluators. And then also those farms were visited on the same day in person by an on-farm evaluator. And so 10 of the farms were visited using a standard telemedicine package by 3 different office evaluators, and 10 of them were evaluated using a specialized telemedicine package by 4 different office evaluators. In the next slide, I'll show you what those 2 packages are and why we named them what we did. We then compared the telemedicine evaluations to 1 in-person evaluation that was done on the same group of pigs on the same day. So here you can see the standard telemedicine package was a handheld tablet and a Bluetooth speaker. The tablet had Verizon Cellular, and then we communicated using that speaker. The specialized package had a technical advantage. We used smart glasses, and so they allowed the person on farm to be hands-free and kind of walk through the barn. In terms of connectivity, the company Distinct created this cellular booster for us, where basically it communicates with the closest cell towers and creates a Wi-Fi signal that we connected the smart glasses to. So we then had both the on-farm evaluators and the telemedicine evaluators fill out the same kind of general clinical picture, where they recorded the primary system affected, primary clinical signs. We limited that to 3 just to have the most prevalent clinical signs represented. And then they recorded the prevalence as a percentage of pigs in the pen that were affected with that clinical sign. We then had them record the primary problem for intervention. And so what we did here was compare the in-person to the telemedicine evaluations. And so this slide shows overall agreement. We defined overall agreement as the on-farm evaluator and the telemedicine evaluator had the exact same clinical signs listed. So they listed the same 3 clinical signs for each farm. So the chart here, you can see there's 2 different bars. One is for standard telemedicine package. The other is for the specialized telemedicine package. And then on the y-axis, it's a percent of all evaluations. So each bar goes up to 100%. And so for the standard telemedicine package, you can see that 30% had overall agreement. So only 30% of the standard telemedicine package evaluations had the exact same clinical signs listed as the in-person. When we look at the specialized telemedicine package, it actually performed more poorly. And so 10% of those evaluations agreed fully with the in-person evaluation. And we did see statistically significant differences between those two packages. So I wanted to dig in a little further to understand what kind of clinical signs was causing this disagreement. So the next thing I looked at was high prevalence clinical signs agreement. And so that was defined as the telemedicine evaluator and the in-person evaluator agreed on all clinical signs that were 5% prevalence or greater. And so what we did was we removed any clinical signs that were less than 5% and then recalculated that agreement. When we did that, you can see that our agreement significantly improved. So for the standard telemedicine package, about 90% of the evaluations agreed. And for the specialized package, it still was outperformed by the standard package, but it improved as well to 55% of evaluations had this agreement for higher prevalence clinical signs. So this disagreement piece was concerning to me, and I wanted to understand, is it because the technology wasn't good enough to transfer the clinical signs, or is there just a lot of underlying variation between veterinarians? So to better understand that, I looked at who identified a clinical sign that the other person didn't. And so on-farm evaluators identified a new clinical sign or a clinical sign that the telemedicine evaluator didn't in 41 of 70 cases. But then on the flip side, telemedicine evaluators identified new clinical signs in 36 of 70 cases. So what this tells me is there's a lot of underlying variation and subjectivity to what how people interpret clinical signs that may not be related to the telemedicine or the technology itself. So in conclusion, from this study, our current techniques really work well for kind of the basic objective checklist and auditing approach. However, we did have poor agreement on clinical sign interpretation between on-farm and telemedicine evaluations. As I mentioned, new clinical signs were detected frequently, both by the on-farm and the telemedicine evaluators, but that agreement improved with higher prevalence clinical signs. Again, I think that the camera quality and hardware can impact agreement. As we saw, the standard package outperformed the specialized package. And when we dug a little deeper into the specs, the tablets had a higher quality camera than the smart glasses. And so I think we saw that in our data that we provided maybe better, more accurate photo quality and video quality in that standard package. So throughout these two studies, we noted some limitations to how color is transferred through telemedicine. So the slides here, the photos here, in each of these photos, at least two of the pigs in the photo had dark blue treatment marks on their back that were easy to see on farm. And as you can see in these pictures, they're not easy to see when you're sitting on the other side of a telemedicine console. So this led to my final study where we looked at an evaluation of color transference for synchronous and asynchronous telehealth methods. As I mentioned, we identified that there was kind of a limitation in how color was coming through. So this study, the objective was to characterize the accuracy of 3 telemedicine techniques in transferring objective color and location mark on a pig from the farm to the office. So we initially did a pilot study where we marked a whole bunch of pigs with different colors in different locations. And then we met via telemedicine and basically to see what colors and locations we could see. Through this, we identified the most and least transferable location and color combination. So the most was this top photo, which is red on the pig's tail, and the least was this bottom photo, which is orange on the pig's flank. We then did a prevalence study where we marked 14 pens of about 80 pigs per pen. They were randomly assigned to one of the 2 color location combinations, and then we had a prevalence percentage represented. So we had 0, 1, 5, 10, 15, 20, and 25. And so we randomized the order of those through the pens so that the evaluators didn't see a trend and start to better find those marks in the later pens. We then enrolled 29 veterinarians and assigned them into one of 3 treatment groups. The first was a synchronous group that viewed the pigs live through like a video call. The second was an asynchronous group that watched 1080p video. And the third was an asynchronous group that watched 4K or a higher quality video of the pens of pigs. Each participant recorded the color and location of any marks they saw, and then the prevalence or percentage of the pigs in that pen that they thought were marked. They also recorded the time they spent in each pen. This was our pen assignment. So again, we had 14 pens. Each color and location of mark was represented at each prevalence percentage. When we dig into the results, so this slide kind of shows you the color transference. On the left, we have the red tail pens, and so the pen ID is across the bottom. R stands for red tail, and then the number is the percentage of pigs in that pen that were marked. The y-axis shows the percent of correct mark interpretations. The graph on the right is the same thing, but for the orange flank pens. And really the takeaway from this slide is that the asynchronous 4K had the best color transference. And then it stepped down from there to the 1080p asynchronous group. And finally, the poorest color transference was seen in that synchronous group. And then as we expected, the red tail marks transferred better than the orange flank marks. We then looked at if they found the marks, what did they report as the prevalence or the percentage of pigs marked in that pen? And so again, across the bottom, we have the pen ID, and then here is our average reported prevalence. So if we just look at this R20 pen, so that means that 20% of the pigs in that pen were marked with red on the tail. Even if the veterinarians saw the mark, the average reported prevalence was about 8 for each treatment group. And so we significantly and consistently underestimated prevalence of those marks. So in conclusion, the methods in this study did show limitations to color transfer. We also underestimated the prevalence of marks for each method. So really kind of where do we go from here with this research? In summary, we supported a few different use cases, including transferring clinical skills via telehealth, as well as capturing objective site data. We also identified use cases that presented challenges through this research and things that need to be worked on further before it's used consistently. The first was evaluating clinical signs, and the second was estimating prevalence within a population. And some of these limitations could really impact surveillance and diagnosing of disease when using telemedicine. So our future work, I think it'll be important to focus on post-mortem necropsy and tissue collection via virtual instruction, as well as for the pig evaluation component, evaluating the underlying differences in veterinary interpretation of clinical signs. So we understand what that baseline subjectivity is. And then again, evaluating pigs with disease epidemics. So with higher prevalence of clinical signs, does that change our agreement? I'd like to acknowledge those that funded this work, the SMEC team who did a lot of the data collection and long hours on this, the farms that collaborated with us, as well as my PhD program of study committee who helped design these research projects. And so with that, I'll stop, and I think we're doing questions at the end.
Thanks, Meredith. Yep, just a reminder as Dr. Zimmerman brings up his slides to please put your questions in the chat and we will address those after he wraps up his portion.
But Meredith, you can see my slides?
Can you go to display settings up there in PowerPoint and just duplicate because we're seeing your side by side.
Okay.
So if you click on, oh. You can go back to your presenter mode. And then up there, do you see display settings in the middle top?
Yes.
And then just duplicate.
Okay.
Perfect.
So, um, thank you, Stacy, for giving me the chance to talk about this stuff. What I want to talk about is actually a lot for a short presentation. So anybody who would like a copy of this presentation or other information from this presentation, this is my email address. I'd be glad to share it with you. So U.S. SHIP practical approach to regional surveillance for notifiable diseases. By region, we are trying to say it could be a state. We may want to surveil a state or a county, or in this case for U.S. SHIP, we're really talking about surveillance of the U.S. The information in this talk has been published. This is the publication. Again, shoot me an email. I'll be glad to send this to you. Let's start out with saying who or what is U.S. SHIP, and hopefully most of the attendees know who U.S. SHIP is. But just in case you don't, U.S. SHIP is the Swine Health Improvement Plan. Its goal in shorthand is to support continuity of business in the event of a very bad day. So if foreign animal disease shows up in the U.S., support continuity of business in the areas outside the state or the area affected by that FAD. It's a very collaborative organization. It includes all elements of the U.S. pork industry, from small to large producers, packers, and state and federal animal health authorities. And it has a predecessor. It's really modeled after the National Poultry Improvement Plan, which has been around since 1935. NPIP was originally formed in 1935 to control pullorum disease, but it does provide an excellent model for us. The U.S. SHIP organization is highly dynamic. Everything starts here in the House of Delegates, and that includes the official representatives of the U.S. SHIP. Among those are, of course, the producers, the packers, VMOs, and others. This is where the decisions are made at the House of Delegates, and then they are implemented by our state and federal animal health authorities in conjunction with our producers and packers. This is a House of Delegates meeting. On the left, you see the National Poultry Improvement Plan, one of their House of Delegates meetings where the participants, the official participants, are raising their hands, voting on some matter. Here on the right, we see the last House of Delegates meeting of the Swine Health Improvement Plan. Again, they're raising these placards as official representatives of the meeting. So why are we concerned about notifiable pathogens? And by notifiable pathogens, I'm talking about those pathogens listed by OIE, or what's now known as the World Organization of Animal Health. They are concerned for us. We tend to be, we kind of live in a bubble here in North America, but in fact, a lot of these pathogens are still very active. They're doing business perfectly well, thank you. This is 2023, 67 of the 183 OIE members are free of FMD. That's only 36%. And so you see FMD is doing quite well. Here it is, inflicting between $6 and $21 billion of damage every year. Here's classical swine fever virus eradicated from the U.S. in 1978, but still doing very well in the rest of the world. Only 38 of the 183 members are free of classical swine fever virus. So it's circulating quite nicely. And of course, our new nemesis is African swine fever, first introduced into the country of Georgia in 2007. Subsequently, 60 countries have reported African swine fever outbreaks. And in just the period 2021 to 2023, 11 countries reported their first outbreak. So it continues to expand. Here's Haiti and the Dominican Republic in the Caribbean. We don't have Sweden marked here. Sweden had an outbreak last fall. So African swine fever continues to move. Do we need surveillance? We do have other surveillance streams, but specifically does U.S. SHIP need to implement surveillance? I would argue yes, and I just want to give you some background on that. This is our good news. As an industry, we're doing quite well. our product is in demand. Here on the bottom, we see exports of meat and byproducts in metric tons. Metric ton is 2,000 kilograms. And you can see that compared to 1961, our current data, well, these data are from 2022, 15 times as much product was exported as was exported in 1961. Here we see in blue, in a blue line, the exports of live pigs. You might be surprised about how many live pigs are actually moving around the world. It's 14 times more live pigs being exported between countries as were exported in 1961. And here we see the total global inventory of pigs, which is only 3 times what it was in 1961. This is showing movement of pork products, and pork byproducts in 2020. And I have legal underlined here because I don't know if you follow the SHIC newsletter that comes out every month on the international events, but it's very common for them to report that some quantity, sometimes tons, of illegal product have been detected. In most cases, those products are not tested, but in too many cases, when they are tested, they are in fact positive for African swine fever or something else. So there's legal and illegal trade. The illegal trade in particular is troubling. Here's just to give you some numbers on live pig exports and live pig imports. So these are between countries. We're not recording what's happening within countries. You can see for this period, 2022, 47 million pigs, 47 million live pigs were exported from some country. These in the top 20 are the recipients receiving about 40 million of those 47 million that were exported. A lot of pigs moving. For the US, this is movement, internal movement. So this is in shipments. These are official USDA reports. They're based on health papers. So when pigs are moved between states, health papers are filed. And you can see we've always had some level of in shipments, pigs moving between states. Prior to 1990, they were typically in the 3 to 4 million per year range. You can see that we had a shift in the industry. We first see here in 2000, we jumped from 4 million in shipments, like pigs move between states, to 24 million in the year 2000. And now in 2022, we're up to about 62 million pigs being moved between states every year. So we have this rapid movement between states, which means that we can't take our time at detection. We must be on it very quickly. So we think we will see them. And what I'm referring to here is syndromic surveillance, that is seeing new things based on clinical signs, identifying whether it's African swine fever or foot and mouth or whatever on the basis of clinical signs. That's much of the way we think we're going to do surveillance, but it has never worked very well. This is such a classic example. I included that. Here's African swine fever in Brazil in 1978. So here's a guy, this is a real story. He got his airport security officer who also happens to have a few pigs at his place. And so he collects the food scraps off airplanes, takes it home and feeds it to his pigs. And the bad news is one of the planes he was collecting from was coming from Europe at the time that Spain and Portugal were still infected with African swine fever. So he feeds his pigs and they get sick, but they're misdiagnosed as having been infected with classical swine fever virus instead of African swine fever virus. From April to December, the virus disseminated from here by Rio throughout the length of the country. And finally, in 1984, it was eradicated at a cost of $21 million. You better add a 0 or 2 on that if you're going to have today's costs. Here's FMD in the UK. FMD has actually been mistaken as something else quite a number of times, sometimes a BVD or other pathogens, other diseases. So here's FMD in the United Kingdom in 2001. So the infections started happening, and these animals were being moved across the country. Travel is a huge thing. Moved across the country in hundreds of separate travel movements, spread the disease everywhere, and the cost of controlling the outbreak was $4 billion. We have examples closer to home at how quickly these pathogens can move. Here's an example of PDV. It arrived in the US in 2013. is actually been traced back to Asia where it came from, north and south. So we are not immune from this effect of travel. And we have this recent example of H5N1 in dairy cattle, reported first on the 25th of March, and already by the 11th of April, it had been in 8 states, moving very quickly. So the speed at which these animals are moving is part of the problem, part of the reason that we need better awareness. This is a graphic, kind of what we're trying to achieve. There's an introduction, and then there's the spread, and at some point in time, it's too late, like we saw with PDV. It moves so fast, and so we need to have some kind of method in place to achieve early detection. Detection early enough to close down the affected sites and eradicate whatever pathogen we're dealing with. So it's important to think, people think, well, we've already done surveillance in the past, so why not just keep doing what we did in the past for the classical swine fever eradication or pseudorabies eradication? So my message here is what we did before is not going to work the next time. We need a new plan. And the big reason is we're not the same industry. You saw that before with in shipments. We had 4 million pigs moving across state lines in 1990 and 60 some million in recent years. So, but this is kind of snaps, or it's a snapshot of how the industry has changed. You can see here in 1920, we had about 5 million farms with hogs, and then we've had this long slide. So in 1961, when we started the classical swine fever eradication program, the average inventory on a farm was 50 pigs. Each farm had an average of 50 pigs. It's hard to imagine now. Here's 1990, we started the pseudorabies eradication program. Average farm inventory was 250 pigs. And so from here, you can see this green line, which is the number of pigs on a farm, is beginning to go up here during the pseudorabies eradication program, and it just keeps escalating. So we're a much different industry than we were previously, and we keep evolving. See, we've already seen this. Just to make a note, 14 times more pigs moved in 2022 than in 1990. So here's the way we typically think of our farms and of surveillance as this some kind of tranquil pastoral theme. I like this picture. This is Roswell Garst, who some of you have undoubtedly heard of, from Coon Rapids, Iowa. He was an entrepreneur. He started Garst Seed Company, which later became Syngenta Seeds. He's strolling around, and you can see he's got pigs running with cattle, which we would never do anymore. He's strolling around his place with Nikita Khrushchev. Khrushchev and Roswell Garst became friends, probably in quotes. But Nikita Khrushchev came and spent a weekend at Roswell Garst's place, brought his wife, brought his daughter. They had a good time. So we've got this dream on the left, and the reality is, in our current industry, we have this tremendous rush of pigs, people, trucks everywhere, crossing the countryside. And so surveillance is more like this and no longer this quiet pond on the left. So how do you surveil this onrush of pigs and people and trucks? Because we do have these problems we have to address. We have 61,000 farms according to the most recent Census of Agriculture, 74 million pigs, and a whole lot of space to keep track of. So what U.S. SHIP is proposing is a change in focus. For our previous eradication programs, previous surveillance programs, we've always worked at the herd level. You try to prove the status of each herd. Are they negative? Are they positive? You try to prove what is each herd, positive or negative. And based on that, the region is either negative or positive, right? This is an endless, fruitless task, again, because everything is moving so fast. A herd can be negative one day and positive the next because they have new pigs, they have had more trucks, they've had more visitors, et cetera, et cetera. So change the focus from each individual herd to the region itself. And so this little publication that I mentioned earlier, the title is Active Participatory Regional Surveillance. Active means targeted sampling of poor doing pigs Participatory because the people on the farm collect samples and submit to the NALM labs, the National Animal Health Laboratory Network. The NALM lab was set up after 9/11 specifically to address the risk of foreign animal diseases, and regional because the test results are interpreted at the regional level, not at the individual herd level. Active, participatory, regional. Active, targeted sampling of poor doing pigs. That's a funny thing. We've always done random sampling, or at least in the recent past. That came out of the pseudorabies eradication program. Active, targeted sampling of poor doing pigs is actually an old statistical technique. There were a lot of publications in the 1920s and 30s on targeted sampling. And most recently, the European Food Safety Authority, in one publication on African swine fever and one publication on classical swine fever, is recommending targeted sampling to improve the probability of detection. The problem with random sampling is you have too many samples from negative pigs. You can improve your chance of detecting your target if you sample the sick pigs. And we're saying sick pigs, not dead pigs, because it takes time for pigs to die. We want to pick them up before they have had time to die. And also, if you have a non-negative sample in your NALM lab, you're much better off if you can go back and sample the same pig or the pen from which that sample came. If you go back and the pig is gone because the rendering truck picked him up, then whoever shows up from USDA is going to feel obligated to do extensive testing both on your farm and on any epidemiological contact farms. If the pig is still there, you can have a definitive answer. It was a false non-negative, or the pig is actually positive. Participatory surveillance. People on the farm collect the samples. They will be collecting them under the supervision of their veterinarian. But we already have people on farms that have a lot of expertise, and we have training programs. Actually, SMEC has been working on these training programs for people to collect samples. So the whole thing is important in the sense that sample collection is the most expensive component of a surveillance system. The most expensive component of a surveillance system. Whereas if we already have our samplers in place on the farm, saves us massive costs. This little map on the right just shows the location of all the NALM labs, and you can see they're readily accessible throughout the country. Of course, our lab at Iowa State is a NALM lab, also the University of Minnesota, as well as South Dakota State's lab. These are all NALM labs that do a lot of swine diagnostics. Easy samples to collect. We already have extensive publications, extensive research on all these sample types and their efficacy for detecting foot and mouth, African swine fever, classical swine fever, and many other pathogens. They're readily collected. People know how to collect them. It's not a big deal. The U.S. SHIP program is recommending collection of 10 poor doing pigs, pooling the samples into 2 samples, or pooling the 10 individual samples into 2 pooled samples. The frequency varies depending on production type. So boar studs would collect more often than regular commercial herds or non-commercial herds. You can see the time frame here. Which specimen will be collected will be up to the producer. If they feel more comfortable with oral swabs or oral fluids or blood swabs, that would be their choice. So the whole thing could be summarized as a few samples from many herds, a few samples, 10 samples from the 10 poor doing pigs, pull them into 2 from many herds in a region. This is an unusual design. I'm not aware that it's ever been used before. So the question was, could it work? So we did 2 things. In the first part, we simulated the disease spread to populate the synthetic database with positive herds. What we did is we just downloaded the CAFO data from these 8 states. We had 17,521 farms in this data set holding 51 million pigs. So this area, these 8 states, are a pretty good size. In fact, they're as big as all of Western Europe, big chunk of China. It's a significant geographical space. The this ADSM software, this is USDA software for simulation of disease spread in livestock populations. It has a lot of variables you can control, and we did that. We looked at starting out the index herd in different levels of pig density, in different production types. We played with the probability of spread by direct contact or indirect contact, and area spread as well. So I'm not going to go through this very much, but we had a total of 2,430 disease spread scenarios, and each one was run simulated 100 times. So this is a graphical representation of the ADSM output, and all these variables are important. They really do affect the rate of spread, and some spread very slowly, and others spread very quickly. This little map just shows you what a 0.3% prevalence in our 17,521 farms would look like. This is actually one of the simulations, and you can see how it spread across the Midwest. The second part, once we had our positive and negative herds, then we modeled the probability of detection. Could we detect these positive farms? Again, we had several variables that we could manipulate. In this case, farm participation, because of course, US SHIP is voluntary. You volunteer to participate, and so we don't know exactly what that level of participation is going to be. So we looked at what happens in terms of detection if 20% of the farms participate, 40, 60, 80, or 100%. And then the other thing is the probability of detection. What's the likelihood that if you sample some sick pigs, 10 sick pigs, that you will in fact detect a herd that is positive for African swine fever, classical swine fever, or whatever the target happens to be? We looked at 10, 20, 30, 40, or 50% probability of herd level detection. These figures are actually quite conservative. I mentioned to you before that the European Food Safety Authority has these two publications, one on classical swine fever, one on African swine fever, and they're recommending targeted sampling. And in their publications, their simulations achieved about a 90% probability of detection after 2 weeks. So these are very conservative figures. But let's see what happens. So here's the results of these two analyses. First, the spread of disease in our population, and second, the probability of detection in our population. Here's what it looks like if you have 60% of the producers participating at a herd level probability of detection of 30%. We can follow the arrow across. And so here's the line. This line is a probability of detection as a function of the number of infected farms in a region. And you can see we're achieving 90% probability of detection when we have, what do you want to call it, about 12 positive herds in the region. Here's another option. This option is 40% of the producers are participating. And again, a 30% probability of detection in positive herds. Here's this line. And you can see here's somewhere around, call it 18 or 19 positive herds. If we have 18 or 19 positive herds in a region, we have about a 90% probability of detection. Again, this is among 17,521 herds in a region. So that it's quite sensitive. This lays it out a little bit farther, but you can see if you have 40% producer participation and a 30% probability of detection, or anything higher than that, you're quite good in terms of detection. 90% or greater probability of detection. So our goal is to achieve this early detection, achieve detection at a time when we can actually shut things down, clean up infected herds, shut it down before everything is run away. So economics is also a big thing for us. How much is this program going to cost? We didn't do any sugar coating here. We put the full cost in here, and we don't know what people want to do. They can collect serum samples if they want to, and here's our cost for collecting these samples, serum samples. You can collect swab samples. Those could be blood, nasal, oral, or fecal swabs. And here's our cost on a per sampling basis. And then you got to send samples to the laboratory, and that we use the full cost. We use the insulated shipping containers a lot of people use. cold packs, and of course the shipping cost. If you, this is the quick and dirty. Depending on which test is used, so if you look at for antibodies, cheaper than if you look at nucleic acid detection. The cost is between about two cents per pig in the region up to 3 cents per pig in the region. And here's our cost. We said $25 for a PCR and $7.50 for an antibody assay. This is one area that I think we could improve upon a lot, because there's cheaper ways to sequence these samples. I think we could optimize this quite a bit. So I think probably we could end up with a cost of between 0.5 cent and 1.5 cents per pig in a region. But this is, again, not sugar coated. This is what we're working with right now. So a few samples from many sites is highly sensitive. You can detect an extremely low prevalence at a herd level. Plus, it fits our fast-moving industry. We want to maintain continuity of business. We can do that in this kind of approach. It's diagnostically sensitive, but pretty cost effective, and it's highly adaptable. It could fit any variety of pathogens, including our nemesis, African swine fever and classical swine fever. And the other important part is we don't have to invent anything. All these parts are in place. We know how to collect these samples. We know how to ship them in. The laboratories are in place. The Dawn labs were created in 2002 exactly for this purpose. They are connected electronically with both with each other and with USDA. So reporting is really fast. Plus, they're connected already to our clients, our producers. Electronic reporting is usually within 24 hours. So it fits everything we have. So again, a better analysis, a more thorough analysis is available here in the publication. You can find it here. Here's the DOI, or send me an email and I will be glad to share with you. I like this quote: simplicity should be a guiding principle for surveillance. It should not be complicated. Anybody should be able to understand it. And there's no questions about who's doing what, when, where, or why. So, Meredith, that's what I've got.
Thank you both. So I just put in the chat both speakers' email contacts, because we are pushing up right against 1 o'clock right now, and I know our speakers have a hard stop at 1. So you can feel free to contact them directly. If anybody has a quick question, you can put it in the chat now. Otherwise, thank you all for joining us today, and I hope you have a great rest of the week. Okay. Well,
All
thank
right.
you
for having us.
Very
Thank you
much.
both.